and then when we appear at the last level, which is final expression or result, most of the time for the tree level at least, it is again simple, right. So this intermediate step here, that is creating all the problem in the calculation, right. To give you a concrete example, say for this kind of action, which is basically f mu nu a, f mu nu a, okay, the gluonic part. Here there is a gauge redundancy, which is basically, if I change a mu, like say u a mu u dagger minus I by g del mu u u dagger, then everything remains same, right. But because of this this gauge redundancy, we get some complicated terms, okay. To be specific, for the self interaction between the gluons, so it gives you some unphysical or superficial degrees of freedom, okay, that ultimately does not contribute in the full calculation, okay. And this basically give you some non gauge invariant term, okay. And this non gauge invariant term ultimately does not contribute the final calculation, because you apply the local SUN symmetry, okay. But at the intermediate step they appear, and that is why we get the complicated expression at this level, okay. Now the question is, can we simplify it further so that we do not have to deal with so many terms in the intermediate step? And the answer is yes, if we consider the helicity formalism, okay. So before I describe the formalism, let me give you the usefulness of this formalism by checking how many number of terms will come if we go in the canonical approach and if we go in the helicity formalism, okay. Okay, so to give that, suppose we are considering Gg going to n number of gluons, okay. Now if I make a table, it goes as, so this is 2 to ng, and here I am writing the number of n, and here I am writing the number of diagrams, okay. Now for 2 to 2 gluon, the number of diagram is 4, okay. 2 to 3, it is 25, 2 to 4, it is 220, 5, it is 2485. So you see how gradually they are becoming complicated. And if I go as in my note it is written, I can write it down further. So 34300, 559405, this is the last, 10525900, okay. Yeah, No, most likely it goes like n factorial or something, right? But no specific relation.
So they have actually drawn and counted.
Hmm?
They have drawn the Feynman diagram and counted.
Yes, exactly. Yeah, right.
2 to 1 is possible as well, right?
2 to 1.
2 to 1
But the massless dynamically.
I am considering scattering, so 2 to 1 is not a scattering. Right?
Kinetically is not a.
But anyway, yeah. So you see, for this process, say, okay, this is too simple for this process, say. So the amplitude contains at least 25 terms, right? So amplitude square contains at least 625 terms, right? At least, okay. Now if I go to the helicity formalism, what happens here? Here, so gluon is massless, right, and it can have only two polarizations. I will denote it as plus and minus, right. So 2 to n gluon, how many possibilities could be there? 2 power n plus 2, right. So in the amplitude I have 2 plus n plus, sorry, 2 to the power n plus 2 terms, right. And in the amplitude square also I have 2 to the power n plus 2 terms. That is the beauty of this method, because different helicity combinations, they do not talk to each other, okay. So for 2 to 3 I can have 2 to the power 5 terms, right. But you remember that QCD is a charge conserving and parity conserving theory, right. So suppose if you calculate a specific combination, say GG going to GGG, this is plus, this is plus, this is plus, minus, minus. From this expression I can easily get GG minus going to G plus plus, okay, because this is just the parity switch of the gluons, right. So basically it is not 2 to the power 5, it is 2 to the power 5 by 2. So it is actually 2 to the power 4. Charge and parity conservation, yeah. So this is only 16 for the helicity formalism, but it is 625 at least for the usual canonical approach, yeah.
It would happen that the term you are mentioning for the helicity techniques, it may have the large expressions. In compared to the, like when you say it is 25, there may be expression are shorter.
This is just a rough estimation. I mean, at least this many terms will appear, right. Now there will be cancellation or whatever, that I don't know, but in this case the number of terms that appear will be only 16, right. You get my point. I mean, this is
Number of times these are the possible helicity combinations.
yes.
But in each helicity combinations, the amplitude file can be large.
I am not getting your point. Can you explain a bit?
When you assign the helicity and
Yeah.
then you calculate the helicity amplitude,
So
that particular
I am assuming that for this helicity I have only one term, say. Okay.
So one term, when you say the term, in terms of all
So this is not a one-to-one correspondence, what you are telling. I understand your point. This is just giving you a rough estimation that here you have to deal with very less number of terms compared to the other approach. Okay.
So why A and A square is the same number of terms in helicity?
Because if you square this and if you square this, there will be no square, because this kind of interference term, they are absent in this theory, okay. So no interference term will appear, only square will appear, okay. So yeah, this is the beauty of this formalism, okay. Now should I erase this? Yeah, okay, fine. So now what I am going to tell you, that everybody knows, some quick recap of what we have done in the quantum field theory course. So we start with the Dirac equation, okay, and that is I del slash minus m psi is equal to 0, okay. Now as you know from your quantum field theory course, this is a solution of the Klein-Gordon equation as well, this psi, right, because if you multiply I del slash plus m on both sides, it will give you box plus m square psi, okay, and this psi can be written in terms of plane wave expansion, yeah. So this psi is basically u e to the power minus I p dot x plus v e to the power I p dot x. All those integration over p and everything is understood, okay. Now if I apply this here, I will get the momentum space Dirac function, and they are like p slash minus m u is equal to 0 and p slash plus m v is equal to 0, okay. Now for massless fermions, u and v, they are at the same footing, okay, and as you know, and they have two solutions. So we write us, where s can be plus or minus, or vs, where s can be plus or minus, okay, because this is spin-up particle. Now so this p slash, you know, that is basically p mu gamma mu, okay. Now for this gamma mu, there are many representations, like Majorana representation, like Weyl representation, like Dirac representation and everything. So we will use the Weyl representation of gamma mu. And what is that? Gamma mu is defined in this representation as 0 sigma mu bar 0, where this sigma mu is basically identity minus Pauli spin vectors, okay, and this is 4 cross 4 matrix, okay. Now if I do p mu gamma mu, what I will get? I will get p mu here, right. Now if I multiply u here, so I can take u as u plus and u minus, okay. So what I will get? I will get p mu sigma mu u minus is equal to 0, right, yes, and p mu sigma mu bar u plus is equal to 0. So basically you see, instead of writing u plus and u minus, if I would have written this as u plus 0 and 0 u minus, I would have arrived at the same solution, same equation, right? So that means these are the two independent solutions of the u, okay, and this u plus and u minus, they can also be achieved through a projection operator, which is defined as, say, gamma r or gamma l, where gamma r is basically half 1 plus gamma 5 and gamma l is half 1 minus gamma 5, okay, and u plus minus is equal to gamma r or l u, okay. Similarly, there exists relation for the u bar, and by inspection you can easily get what the expression would be for u plus and u minus. Okay. Before that, let me write the convention that is usually used in the literature. So u is like this. Sometimes it is written as, so this is function of p, p, p. It is sometimes written as like this as well, okay, or in this notation sometimes pa, pb dot, or it is written as, wherever there will be plus it will be angle, wherever there will be minus it will be square. So I will be using this notation throughout. Okay. There are some indices, spin indices. You can. I never use this notation, but people like to use this. Some people, yeah. Okay. Some SU2 indices. Okay. Similarly, u bar is u bar minus plus, which you can write it as p minus p plus pa pb dot is equal to angle p and square p. Okay, fine. Now, how the solution would look like? That is very simple. By inspection you can easily get what would be the solutions. So u plus p is equal to root over p plus root over p minus e power I phi. I will tell you what these p plus and p minus are, and u minus p is 0 0 root over p minus e power minus I phi and minus root over p plus. Okay, where this p plus minus is basically p0 plus minus p3, and e power I phi is equal to p1 plus minus I p2 divided by root over p plus p minus. Okay. For completeness, let me write down the u bar also. This is e power phi, e power I phi. Okay. Yeah, bar. Okay. So bar is 0 0 root over p plus root over p minus, yeah, e power minus I phi. Okay, and u minus bar is root over p minus e power I phi minus p plus 0 0. Okay, and here the normalization is like u plus minus dagger u plus minus is equal to 2p0. Okay.
Sir, like in the direct equation we got like square root of p dot sigma. Is it coming from there?
Yeah, exactly. Or the easiest way is you put it there and you can satisfy all the equation of motion. Okay. All right. Yeah. Now one interesting thing to see is that this u plus p, which is written here, can be expressed like this: 0 0 0 0 times 0 0 root over p minus e power I phi minus p plus. Okay. And this is nothing but I gamma 2, right? Because gamma 2 was what? Gamma 2 was minus sigma 2 in my notation, right? So that is exactly I gamma 2. Okay. And this is nothing but u minus p complex conjugate, right? So you see this u plus p and u minus p, they are related through I gamma 2 and complex conjugate. That is basically the charge conjugation of the theory. Okay. Only for the massless. Yeah. So whatever I will do for the massless only. And the spinors that I described, I mean all these solutions, they are for the massless only. Okay. So I started from p slash u is equal to 0. No, I mean here I cannot write down the expression.
Yeah.
But yeah, charge conjugation is high. Right. Yeah. But this is not, these would not be the expression for that. Yeah. Okay. Now okay. Now from this expression it is easy to see that this, which is basically okay, I erase that. Okay, maybe this is u bar pi and that is angle means minus u plus pj. This means that actually, right? That is the notation I will be using. Okay. And if you know the expression of u plus, you know the expression of u bar minus, you put it here and you will see that this is equivalent to minus ji. Okay. So that means this, similarly it is for I angle j is minus ji. Which one? This one? From there actually. So you have expression for u plus and you have expression for u minus bar, and if you put that, and also in this case, so this is basically minus, what is that, minus pj bar u plus pi. So this and this, that will be equal.
From this prior notation, no?
Yeah.
What is the corresponding u?
Okay, yeah, that I should write it down here. Okay, so u pi. Okay, let me write down it in a clear notation that I will be using very often. Okay. So this part, so let me write it down in this fashion. So outgoing plus helicity fermion, that is basically pi plus, which is square. Okay, outgoing minus helicity fermion, that is pi minus, okay, incoming plus helicity fermion, that is pi plus, which is incoming minus helicity fermion, that is pi minus, which is, this is the notation. And also let me write down for the anti-fermion case. So outgoing plus helicity anti-fermion, which is pi minus, and that is square, outgoing minus helicity anti-fermion is pi plus, that is angle, incoming plus helicity anti-fermion, that is pi minus, yeah, that is angle, incoming minus helicity anti-fermion, incoming minus helicity anti-fermion is pi plus, which is square. Okay, so this is the notation. Okay, now if you do this simple exercise, you will get that if I switch I and j, it will appear with a minus sign. Okay, so that means that easily tells me that this II is 0, and so is II with square bracket. Okay, they are antisymmetric, right? Again, as I know the expression of this, if I apply it here, so what do I get? I get u bar minus is what? Root over p minus, so pi minus e power I phi I minus p plus 0 0 times u plus, which is root over pj plus root over pj minus e power I phi j 0 0, which is basically root over pi minus pj plus e power I phi I, right? Yeah, minus root over, this is pi plus pj minus e power I phi j, right? this simple exercise, yeah, and this can be written as Sij e power I phi ij, where this Sij is basically Pi plus Pj square, which is for massless particle Pi dot Pj, okay, and cos phi ij is equal to P I plus Pi1 Pj plus minus Pj1 Pi plus divided by root over Sij Pi plus Pj plus, okay, and sin phi ij is equal to Pi2 Pj plus minus Pj2 Pi plus divided by the same denominator Sij Pi plus Pj plus. This you can take it as an exercise. This is easy to show, okay. So the main point is that erase this part. Okay, so the main point is that this Ij is basically square root of Sij e power I phi ij, right. Similarly, you can do the same exercise for the square bracket and you will get, okay, you will get e power minus I phi ij, okay.
What is this one notation?
The first the x component of here, okay, and plus is P0 plus P3,
That is why.
that is y component, yeah, okay. Now from here it is maybe I am making a mistake with the sign, yeah, right, okay. So the main point is that from here you get a very useful relation, Ij angle Ij square is equal to minus Sij, okay. So that is one useful equation. Other useful equations are the Schouten. So this helps in simplifying the results, okay. Schouten tells you that if you have multiplication of two spinor products, angle or square with the same thing, it is similar to AD CB plus AC BD. Same is true for when it is a multiplication of two square spinors, okay. And one more thing which is very useful is the Freer's identity. Freer's tells you that if you have some multiplication, right, like A gamma mu B and C gamma mu D, then it is basically 2AD CB, okay. In other words, if you multiply say gamma mu with this quantity it is basically 2 okay. Now we are ready to calculate some specific example. Okay, one more thing. Yes.
How this identity can above ABCD can be derived? Like
These ABCD means they are like I, J, K, L. So what is the question?
like how it can be derived only using that? You don't know anything else?
Oh, this sorted identity. That you can easily check using the explicit form, but there are other ways also to derive this. I am not doing the derivation, just giving you the useful results. Okay. One more thing before I proceed to a specific example is that, so these are for the spin half particle. Okay. Now in the same spirit, the polarization vectors, say epsilon mu for the gluon or photon, they also can be written in terms of spinors. Okay. Suppose this is the polarization vector with momenta k, then this is k gamma mu q divided by root 2 qk. Epsilon mu k minus is k gamma mu q divided by root 2 qk with a minus sign. Any questions here?
How are you writing this polarization? What's the motivation?
That we will see. Yeah. But no questions. What is q? Because I have only k. So q is any arbitrary massless vector, which is sometimes called reference vector, and that is basically a strong check on your calculation. Whatever you calculate, the result should be independent of this q, the choice of q. Okay. Yeah. That should not be. That should not be k. Yeah, right. Sorry. Yeah. Good. This should not be k. Yeah. Okay. Now I'll work out a specific example, and there you will see the usefulness of writing the polarization vector in that form. Okay. Okay, let it be here. Fine. So the example I will take. Any question? Yeah.
This polarization.
Mm-hmm.
I should get the summation over actual polarization is minus infinity plus.
Yeah, that is a good exercise actually. That you can always check. Yeah. Okay. Yeah, and also this epsilon, you can easily check that epsilon dot k is equal to 0, epsilon plus minus star is equal to -1. All the relations they follow actually. Okay. Now the example I'll take is say E minus E plus going to photon. Suppose the momenta are P1, P2, P3, P4. Okay. Now I have two diagrams for this. This is 1, 2, 3, 4. This is 1, 2, 4, 3. Yeah, just a minute. Yes.
So this identity
only used for computation, or it is actually true in the sense like
That
we are,
again,
yes,
yeah, it is true.
so we are writing sort of a vector in terms of
Spinors.
ah,
Yes, but left side is vector, right side is also vector. But we are representing it in terms of angle and square bracket. That is always true. There is a name, it is called Van der Waals identity or something.
So that is a representation, not identity.
Yeah, same actually. Okay. All right. Yeah. So now I have to calculate this. Fine. I may make mistake with I and minus, but anyway, let's proceed. So suppose this is mu, this is nu. Okay. Now, so let's say this is diagram 1 and this is diagram 2. Okay. So my I m1 is basically what? So P2 is antifermion incoming antifermion with, suppose this is plus plus. Okay, let's take that. Okay. So in that case M1 will be what? So P2 is an antifermion with plus helicity incoming. So incoming plus helicity antifermion is angle, right? So I will write it 2. Okay. Now this is, there is a gamma mu here, right, and there is a epsilon mu here. So I can write it as epsilon 4 slash, right? Huh? Okay. Now this propagator is P1 slash plus P3 slash divided by S13, right? Now I have epsilon 3 slash, and then I have one fermion incoming with positive helicity, that is again angle bracket from there, right? Yeah, sure. So this is one antifermion, because this is positron with momenta P2 and plus helicity. So see the rules. Antifermion, this block is for antifermion incoming plus helicity, so that is angle. So angle 2, right? The final particle is fermion plus helicity incoming. So incoming plus helicity fermion is again angle, right? This is angle. I have not fixed the polarization of 3 and 4 yet. Okay. So this is basically, I should write it down in a more clear way. So this is 1 plus 2 plus 3 4. 3 4 I have not yet fixed. Okay. And there is E square, there is I square. Here there is I, here there is I, right? Okay. Now see, this is, the structure is like A gamma mu, gamma nu, gamma lambda V, right? So by definition I have a gamma r attached with this, right, because these are angle. Okay. So here also I have a gamma r attached with this, sorry, V, right, gamma mu, gamma nu, gamma lambda, right? Now if I switch this gamma r here, this will be gamma L, then from here this will be gamma r, and then from here this will be again gamma L, right? So gamma L, gamma r times whatever, and this is 0, right? So any combination for which the fermion and antifermion both are of same helicity, they will not appear in the calculation. This is basically called the helicity conservation. Okay. So whenever a gauge boson is emitting, yeah. No. As usual, these are incoming, these are outgoing.
Then the propagation is negative.
Ah, sorry. Yes, right. Right. So should I take it all incoming?
That's safe, right?
That's it, right? But anyway, let's see what happens. Yes. Fine. Fine. Okay. So the point is that whenever it is both are plus plus or minus minus, they will not appear. Which one? Okay. So let me write it down more clearly. Is that fine, Tanmay? Huh? Okay. Now the second line I can write it as gamma mu, gamma nu, gamma r, gamma lambda, gamma r b. The last step is a gamma mu, gamma nu, gamma lambda, gamma l, gamma r b. Okay. Fine. So I am left with calculating. Yeah.
Massless particles.
Yeah. Everything is massless. Yeah.
Sir, so this will be true even if we had 3 photons in the final state?
Yes. That is
Instead of
always
2,
true.
it doesn't matter, right?
It does not matter.
Okay, so
Work and anti-quark. Sorry. Positron and electron in this case, they has to be of opposite helicity always. Okay. Okay, fine. So I am left with only this kind of combination: 1 plus, 2 minus, and 3 and 4. Right? Okay. Now I want to fix the helicity of 3 and 4. Suppose they are plus plus. Okay. Then I get M1. Okay. Let me write it down, the full thing. So this is 2 epsilon 4 plus slash P1 slash minus P3 slash divided by S13 epsilon 3 plus. Okay, for the first diagram. Yeah.
Can I make a conclusion here, like if any multi-leg process I have and only 2 leg is identical polarized, then it will be always achieved.
For electron positron. If you have electron positron multiple photons,
Yes.
then also that is true.
That's what I mean. Right?
Right. So the point is that whenever a gauge boson is emitting from some vertex, that has to be helicity conserving vertex. So if one is plus, other has to be minus. Huh? Sorry, yes. Now it is 2 minus, so this is square. Right, thank you. Okay, so this is one direct. I should be careful actually. So I square is there, I is here. Okay. And the second diagram I can easily get by switching 3 and 4, right? So this is epsilon 3 plus P1 slash minus P4 slash divided by S14 epsilon 4 plus slash 1, right? Okay. Now you know the expression of plus. Okay. Now if you multiply, okay, so if I multiply the gamma mu with this, then only I will get the epsilon slash, right? And when I will multiply the gamma mu, that will give me the Fier's identity, right? Okay. So if I do that exercise, then what I will get? For the first term, I will get I square 2.
Sir, how this second term came? Actually,
This from the second diagram, 3 and 4 interchange.
but since you have fixed the 3 and 4, since they have same helicity, they are not
No,
identified.
I have to take contribution from both the diagram, right?
No, both diagrams are same if they have same helicity. Like you cannot identify if they have same helicity, right? 3 and 4.
In both the diagram, I have this choice of helicity. I can have this choice of helicity.
You have particularly chosen 3 or 4 cats.
Does it answer your question?
Actually, I wanted to ask, like, if you are going to
minus
two
1 is the
Mhm.
expected combination.
so if
Charo,
they have
the
like
photon.
just like you have drawn here,
Mhm.
these both diagram are
Plus
indistinguishable.
or minus
I mean,
square level.
No, they are not indistinguishable. Both the diagrams, yeah.
Equal sign.
Because it's about basically from which vertex the photon is coming.
Equal sign.
It's just a
Obligatory convention.
At the amplitude level, they are not identical.
The polarization.
Fine. You can ask that if I calculate the cross section and I get 2 photons, how can I tell which one is P3 and P4? That is valid question. I am not addressing that. Here I am just drawing the Feynman diagram and writing the entity. Okay?
both should give the same contribution, right?
No. No.
At the cross section level, they will not.
At the cross section level, you have to take contribution from both the diagram. No?
No, ultimately they will give.
Because you are summing over the final state. Right?
There are interference.
So the difference in the propagated structure.
The propagator is different in these two diagrams. No?
One case first diagram P1 minus P3 is flowing in the propagator. In the second case P1 minus P4 is flowing. So that is the main difference because of which you will have to compare that well. So this you will do anyway.
And you have to take all the superposition of all quantum states, right? Fine. Okay, so yeah, so from the first term, if I expand this epsilon 4 plus, I will get 4 and then the auxiliary vector q4, and the other choice will give me angle contraction with a square, that is 0, right? And then p1 slash minus p3 slash, and then yeah, so this is q 3 q3 1, right, because the other contribution will 0, and I have a √2 times √2 factor, because in Fier's identity there was 2 and here 1 over √2, so I will get √2 times √2. Okay, this is from the first diagram. Okay, from the second diagram I will get 2, this is 3, then this is q3 p1 slash minus p4 slash 4 q4 1. Okay, now you see this p3 slash with 3, this is basically p3 slash u p3, which is 0, right? So I can drop this term. Similarly, I can drop this term. Okay, and the choice of q3 and q4, that is in my hand, right? So I can choose Q3 is equal to Q4 is equal to P1. Then I get 1 1 from both these diagrams, and that is 0. So this contribution is 0. So with the proper choice of reference vector, this contribution is again 0. Okay. So the only contribution that we are left with is of this form. I am 1 plus 2 minus 3 plus 4 minus.
Velocity conservation can tell anything without calculating it.
So yeah, that is a good question actually. So if this is quark and gluon,
To see actually.
so if this is quark and gluon, I would have said yes, I can tell without any calculation, because this Q1 comes from a gluon, right?
Yeah.
And so one gluon with minus, this is plus, this is plus, that gives me 0, right?
Wait again.
I should not
As
make
an amplitude,
So for example, the total helicity of the incoming and the total helicity of the outgoing particle, that is certainly getting violated here, right?
Oh, which one?
Comment can I? So actually, I have
Basically, yeah. So, yeah, tell me, yeah.
I have read somewhere that if all any diagram which has same helicity or one helicity different,
That is
those
0.
will be zero.
That is Parquet-Taylor formula, but that is for QCD.
But for
The equivalent to QD, I don't know.
So we can say no, total incoming helicity should be equal to total outgoing helicity. But here it is violating. We don't have any.
That we cannot say. That we cannot say. Because these are two different particles, right? And for quark it is helicity, but for gluon it is polarization, not helicity. In that sense, yeah. But so the next thing is that I have to calculate this part. Okay. That is again easy. The same exercise. So for now 3 is plus, 4 is minus. So from the first diagram to epsilon 4 minus P1 minus P3 slash S13 epsilon 3 plus 1 angle plus I square 2 epsilon 3 plus 1 minus 4 divided by S14 epsilon 4 minus, right? Yes, 1 angle. Here, yes, you are right, but they are 0. Yes, you are right. Yeah. Okay. So these are all slash. Okay. Yeah. Now I can make the simplification, as I said, that okay, I have to put the expression for this. Okay. So from the first diagram I get two, then this is minus, means Q4 4 1 minus 3, this is plus, means 3 Q3 1 from the first diagram, right? From the second diagram I get 1 4 2, this is plus, means 3 Q3 1 minus 4 4 minus means 4 minus means 4 angle means Q4. Okay, sorry, right? Okay, now I can take Q3 is equal to 1 then the first term vanishes, and Q4 is equal to, so Q3 is equal to 1. If I put, so by taking Q3 is equal to 1, this term vanishes, okay, and now this becomes 1. So I have 1 1 minus 4 Q4, right. Now this 1 1 is basically U bar P slash, so this one vanishes, so I am left with minus 4 Q4. Now I take Q4 is equal to say 2, okay. Now what is my final expression then? My final expression is I square divided by S14.
But you have assumed reference vector here.
Yes, Q3 is equal to 1, Q4 is equal to 2. Okay. So first line is 0. From the second line I get 2 3 1 4 2 4 1, okay, with a minus sign. Is it correct? Which one?
सर जब आप एप्सिलॉन का फॉर्म पुट कर रहे हो नीचे जो टर्म और नीचे
एप्सिलॉन
Yes. For this term it does not matter, but for this term I should have two more terms which are one is plus, right, and one is minus. Which one is plus? So I should have this term. For 3 and for 4 I should have Q4 4. Now Q3 is equal to 1 and Q4 is equal to 2, right? Do you get it? No? These are coming from this this definition of polarization. There was a term in the denominator that I forgot to put. Okay, fine. So this basically gives me I square. Now S14 I can write it as 14 with a minus sign, right? That was my identity, right? Sij is equal to ij with a minus sign, right? Okay, and I can break this term. So this is 2 3 1 4 4 2 4 1 divided by 1 3 2 4. It looks ugly. So this 2 4 2 is basically 2 4 with a minus sign, right? So here there is a minus now, okay. So minus I square, the final expression is 2 3 4 1 divided by 1 3 1 4, okay. And this is the expression of 2 3 4 1 1 4 1 3. Yeah, so this is the expression of m 1 plus 2 minus 3 plus 4 minus. Okay, for the rest I do not need to calculate anything. 1 plus 2 minus 3 minus 4 plus, what this would be? This would be switching of angle to square and changing 1 and 2, right? So this expression will be 1 3 4 2 divided by 1 3 sorry 2 3 2 4. Okay, do you get it? No? Okay. So the point is that if I take the conjugate of this, then what I will get? I will get 1 minus 2 plus 3 minus 4 plus. Now if I switch this 1 and 2, I will get 1 plus 2 minus 3 minus 4 plus. That is what I want, right? 1 plus 2 minus 3 minus 4 plus. So that's exactly same thing I have done. Complex conjugate is basically changing angle to square, and 1 2 flip is just 1 2 flip in between angle and square.
Conjugate, why are you taking?
Because from 3 plus 4 minus I want to go minus plus. Okay.
You should put star or something.
Yes, conjugate means star. Yes, right. The complex conjugate.
I think he just basically wants to calculate another diagram.
Yeah.
This helicity basically I do not want to calculate because it is easily derivable from this calculation what I have done. I am just relating this to that. Okay. Okay. So what is my final expression then for the mod m square? So mod m square is equal to then m 1 plus 2 minus 3 plus 4 minus square plus m 1 plus 2 minus 3 minus 4 plus square plus m 1 minus 2 plus 3 plus 4 minus square plus m 1 minus 2 plus 3 minus 4 plus square. So these are the only non-zero terms, right? Now I have calculated these two. Okay, I have calculated only this one. This is what we can get from here, and these are just the complex conjugate of each other. So I can basically write it as these two terms multiplied with the 2, right? And if I do the squaring, so for the first diagram, what was the expression? So if I do the squaring of this term, say, so squaring, suppose I have 2 3, then if I square it, I will get 2 3 times 2 3, right? So basically minus s 2 3, right? So from this first diagram, what do I get? I get s 2 3 s 1 4 divided by s 1 3 s 1 4. So 1 4 1 4 is gone. So 2 3 by 1 3. Okay. From the second diagram, what was the result? This was the result, right? So this is again s 1 3 2 4 divided by 2 3 2 4. Then 2 3 2 3 is gone. Okay. So this is basically q by t plus t by u. There is a 2. Okay. And now you can do the spin average and all those. Okay. So that is the result. So without doing any trace calculation and anything, I have arrived to the result. So, and I have just calculated only one amplitude, which is this. Okay. So this is basically the power of helicity formalism. Okay. Now should I continue or 10 minutes? Then
No, if you are in the right place to stop, you can stop. Continue, you can continue further.
yeah, maybe then from here I will switch to now q bar going to gluon gluon. Okay. Then in that case also, okay, let me tell you. Yeah, just quickly. Yeah.
So if I want my result in let's say d dimension, then where should I change?
No, you cannot calculate in d dimension from this formalism. Everything is 4 dimension here. I am keeping the gamma phi, right? So
You cannot calculate loop diagram.
that I will show you how to calculate.
Sir, here when you are taking all the helicity possibilities, then you are basically doing the spin average, whatever we were doing in the trace formalism.
Spin average will come here at this point, right? I have calculated mod m square. Now I want to calculate this piece. Then only spin average will come.
But only there will be 1 by 4 factor,
Nothing
nothing more than.
more than that.
Summation part is done.
Yes.
Summation part is done. Yeah. Okay. What I was telling? Yeah. So from here we'll maybe in the next class we'll continue from there. Yeah.
This can be automatized actually by
Yeah. I mean, automatic means you can generate it in QGraph and then
you substitute all the
yeah. So
external X.
exactly. So you write it in terms of angle and space.
Then for each amplitude you can simplify this also using all the ideas. So we don't need to remember it.
No.
Right.
Once you are told it.
Package is spinning.
Spinning, yes.
It does this.
Yeah, that does this.
I have not used, but I came across that it does the simplification.
So that
Like very
generates the diagram and do the simplification. Right? Spinning?
Yes. But using that is not so good.
Using that is not so trivial. Okay, I never did it.
I tried it for
Solve tried it.
So you can generate this in QGraph and
Yes.
substitute
Exactly. So QGraph gives you all the information, right?
Yeah.
You got everything. Just you have to write one time and find your peers. In your
What happens if massive particles? What happens for massive particles? There we don't have helicity.
No, massive particles also you can represent in terms of helicity because suppose I have a massive particle P. Okay. So basically P square is equal to M square. Right. Now this massive particle I can write it as okay. So this is massless, this is massless. Now I can apply the spin helicity formulas. So any massive momenta you can write it as a sum of two massless momenta. Is it minus or plus? I think it is plus. Plus. This is PF. Yeah.
Different relation on when you
From here only you can derive the relations, right?
yeah.
For the massive spin.
Yes.
Yeah.
So why people are doing still Feynman diagrams? Why
No,
not?
Feynman diagram people will use. I have also used Feynman diagram, but the procedure, the calculation procedure, many people use
No, I'm not
this. Many
Feynman diagram. I'm saying Feynman rules.
that also we have used. Feynman rules we have used. I gamma mu. That we have used, right?
My point is, what is the disadvantage of using this procedure?
No, there is an advantage, no disadvantage. I mean,
Disadvantage that two loop.
yeah, and
Two loop you cannot do.
the point is that here you do not have to bother about the interference terms, right? So the calculation will be simpler. Many people use this formalism only.
Another point is that like when your experiment is polarization sensitive, and
There also this is useful.
there you
Yes.
need to compute the polarization.
Yes, exactly.
So there is no way out.
Excellent.
Sir, how to check the gauge invariance in this? Gauge invariance.
That is very easy. That is, maybe you can take it as an exercise. So you replace epsilon 3 with P3 and epsilon 4 with P4 and see whether you are getting 0 or not.
That is trivially zero.
Here that is trivially 0.
It's good by ubiquitous.
Ubiquitous photo. They have all the list of amplitude square.
They also follow exactly the same.
No, their approach is different, I think. They did it in the helicity. I mean, their expression is in the particular helicity configurations, but their expressions does not match with what I told actually. So they took some different approach probably, but the final expression always matches. And so far, what I have calculated.
They have this u plus, u bar minus.
Right. That's how actually question would be. So you specify the helicities. You write down the polarization vector as a column vector, similarly U and D, and then you start computing. So for example, MATLAB, it basically does exactly that. Taylor, exactly.
Taylor is using
wave function.
Yes.
But simplicities I have seen, they also use shorter identity.